topic by solving the Isospin violation of cell interaction for all neutron stars.
So the talk I want to tell you today is how to use all neutron stars to probe the Isospin violating dark matter in the presence of self-interactions. So I divided my talk today into 4 parts. In part 1, I will go through very quickly the evidences of dark matter and the motivation for unique dark matter self-interactions. And then in part 2, I would like to briefly tell you that how a neutron star captures dark matter particle within it, and how the isospin violation can affect the capture rate of the neutron star. On the other hand, if neutron star keeps accumulating dark matter particles inside it, in principle, this bunch of dark matter particles could form a black hole and then consume the entire star. So, based on these ideas, if we could observe any old neutron star and survive with this black hole inside the black hole formed by the dark matter particle inside it, perhaps we can go back and give some constraint or some hints on the dark matter properties. So this would be the topics of my part 3. So after all of these 3 parts, I would like to address a very short summary. Okay, so let me come to my part 1. So there are plenty of evidences for dark matter, such as from the galactic rotation curve, the gravitational lensing effect. On the other hand, based on such observations, assuming dark matter particles are collisionless, and we stuff these properties into the embodied simulation, and in principle, the outcome agrees with large-scale structural observations such as NTHU very well. However, in small-scale structure, so typically speaking, a scale smaller than a few megaparsec, there are some issues, such as a poor cluster problem, the missing satellite problem, and the too big to fail problem. So, in order to alleviate these small-scale structural problems between the simulation and the observation, dark matter self-interaction is introduced. So in that case, the dark matter particles are collisional instead of collisionless. So the energy can be transported between the dark matter particles. So based on the observations such as the Bully cluster, I can give some hint on the dark matter self-interaction perspective sigma chi-cut should lie within this range. And in my later talk, we were assuming that the self-interaction can be modeled by an attractive Yukawa potential with the coupling constant alpha and the mediator mass n5. So besides the astrophysical observation, there are many detectors on the Earth are built on the Earth to measure the direct interaction between the dark matter particles and the standard model particles. So this plot shows the up-to-date constraint on the dark matter baron sections using the C1 count, and as well as the Lux result are also shown on this plot. So the most stringent constraint happens when the dark matter mass is around 50 eV, and the cross-section is around roughly from the 10 to the minus 47 to minus 46 centimeter square. Okay, so now I have briefly introduced some evidences of dark matter as well as why we need dark matter self-interaction. So let me move on to how neutron star can capture dark matter particles. So imagine that there's a neutron star is circling around the Milky Way. So it constantly encounters lots of dark matter particles in the halo. In principle, if these halo dark matter particles can fall into the star due to the strong gravity of the star, then it could potentially scatter with the barons inside the neutron star, the barons such as the neutrons and protons. And after the scattering, if the dark matter particles lost the significant kinetic energy and make its velocity smaller than the escape velocity, then the dark matter particles will be permanently bound inside the star. So this is called the neutron star capture rate of dark matter particles. So such neutron star capture rate, of course, depends on the dark matter property of the environment, such as the local number density, the velocity distribution, as well as the differential scattering rate. So the differential scattering rate describes the microscopic interaction between the dark matter and the nucleon, dark matter and the baryons inside the neutron star. So of course, it depends on the baryon density of the neutron star, the dark matter baryon cross-section, as well as the Fermi-Dirac distribution of the baryons before and after scattering. Because most of the particles, baryon particles inside the neutron star are in general in the degenerate state. But the density distribution and the chemical potential of baryons inside the neutron star are in general not the same, as you can see from these two plots. On the left plot, the neutron ears are much larger than the proton ears. So neutron composes the most of the matter inside the neutron star, as well as these chemical potentials of the neutrons are in general very different from proton. So this, to effectively predict very different the capture rate between the neutrons and protons to the dark matter. So this plot shows the capture rate of a neutron star, assuming the dark matter neutron cross-section sigma chi n and dark matter proton cross-section sigma chi p are the same. So the green dashed line here describes the neutron capture rates to the dark matter, and this red solid line describes the proton capture rate of dark matter. So you can see if these two interactions are identical, and based on these neutron ears are much larger than the proton ears, so the capture rate of dark matter inside the neutron star are mostly due to the neutron capture rate. So there are almost two orders of magnitude difference. This flat line here is due to the Pauli suppression effect, because most of the particles inside the neutron star is degenerate state. So not all scattering could happen. The dark matter particle must have transport enough energy to kick the baryons out of Fermi sea in order to make such scattering happen. On the other hand, if the couplings or the interaction strengths between the dark matter neutron and dark matter protons are in general not the same. So this is called the isospin violation case. So the sigma chi p, the dark matter proton cross-section, and the sigma chi n, dark matter neutron cross-section are in general differ by a factor of isospin violation case. So in that case, even if the neutron ear is much larger than proton ears, however, if dark matter couples to proton is more stronger than neutron, then the capture rate, the contribution of capture rate from the protons could be enhanced and become comparable with neutrons, or even larger than neutrons. So this would be our subject to test that in an old neutron star. So I briefly described how neutron star capture dark matter particles. So let me move on to the situations of those already trapped dark matter particles inside the star. In general, these trapped dark matter particles inside neutron, they will reside in a small spherical region close to the core of the neutron star, and such region is sustained by the balance between the thermal pressure as well as the potential turns due to the visual equation. So this term describes the thermal pressure of dark matter particle, and the term describes the gravitational potential due to the neutron star itself. And this is the self-gravitational turn of the dark matter particle themselves. And this term is the Yukawa potential of the dark matter particles between the dark matter particles, assuming they are attractive. However, this term is a constant, but these two terms are subject to change depending on how many dark matter particles being captured inside the neutron star. So in the early times, when the dark matter particles are not so much inside the star, the right-hand side of this, the left-hand side and the right-hand side of this equation can reach a balance. However, when the dark matter particle keeps accumulating inside the star, the potential on the right-hand side becomes more and more significant. And maybe after a certain point, when the dark matter number is larger enough, the potential turn can overcome the thermal pressure turn. So in that case, this equilibrium cannot be sustained anymore. So the potential turn will overcome the thermal pressure. So after that point, the dark matter particle initiates self-gravitating and become self-gravitating and collapse and become more and more compact point inside the star. However, this kind of gravitational collapse may be stopped by the Fermi pressure. It means that they will collapse, but they will not become a very compact point over a singularity. They will simply stop by the Fermi pressure. On the other hand, because we assume there's an additional attractive contribution due to the Yukawa potential here, so maybe the Yukawa potential plus the dark matter self-gravitating potential, in principle, these two terms can overcome the Fermi pressure, then the collapse will continue. So a black hole will form. So when a black hole was formed, you probably think that the entire neutron star will be consumed eventually. But this may be not always the case. If the black hole mass, the total black hole mass at the production is too small, perhaps the evaporation process will dominate than the accretion process. So the black hole will form, but it will evaporate immediately. So if this is the case, then the neutron star still feels fine. It does not feel any black hole inside it. However, if the total mass of the black hole at the production is larger than a certain mass, then the accretion rate will dominate will be stronger than the evaporation rate. In that case, the black hole will continue growing inside the star, and eventually the star will be consumed by the dark matter forming black hole inside the neutron star. So this would be our ideas. So in the part 2, I briefly tell you how a neutron star captures dark matter particles and the criterion for these dark matter particles to form a black hole inside a neutron star. So let me move on to the numerical result. Now, how can we prove such dark matter properties based on these ideas? Okay, so assuming a neutron star is a 50 year old, and the dark matter interaction can be described by the potential. In the slide, I fix the median. The median mass is around 1 MeV. So these three plots, the horizontal is the mass of the dark matter, and the vertical is the dark matter neutron cross-section. Of course, depends on the dark matter proton cross-section depending on the isospin violation parameter here. From the left to right, the Yukawa coupling becomes smaller and smaller, and this pink shaded region are the excluding region, because if a neutron star lives long enough, in principle it could accumulate enough dark matter particles inside it and form a black hole that eventually consume the entire star. So if the dark matter properties lie within this pink shaded region, in principle we could not observe any neutron star with a few giga-year-old. However, if we do observe such neutron star with giga-year-old, then we can simply exclude this region based on the observations. On the other hand, this solid line, this exclude region enclosed by the solid line is based on the isospin violation with this value. This value means the dark matter coupled to proton is much stronger than the neutron. So of course, in this case, the capture rate contributions from the proton is comparable or even larger than the neutron contribution. So, of course, the excluded region by the isospin violation case is much larger than this dashed line, which is isospin symmetry case here. So this is the fixed M5 case. On the other hand, this slide shows these 4 plots in this slide are the same as the previous one, but this time we fix the Yukawa coupling. However, from the left to right, from top to down, the immediate mass becomes heavier and heavier. So you could see from these figures, these plots that the heavier median mass was significantly broader than the excluded regions, according to the numerical result. On the other hand, the isospin violating case is region included by the red solid lines, of course, much larger than the excluded region due to the isospin symmetry case. So this will be our numerical result. So let me briefly conclude. So we see from the calculations that even neutrons, neutron yield, or the neutron fraction is much larger than the proton fractions inside neutron star. However, if there's any isospin violation, which means the dark matter coupled proton is much stronger than coupled neutron, then the contribution of capture rate from the proton will be significantly larger. So in that case, it makes that even the proton fraction is much smaller than the neutron, but the contribution from proton is much significant. On the other hand, by considering the attractive Yukawa potential, the dark matter could form a black hole inside the star. So in that case, this kind of property can be tested by future observation. On the other hand, in our calculation of capture rate, we only consider the contribution from barons. There are also other light particles, such as electron and muon, we did not take into the consideration. So if we include these parts, the contribution from these particles, perhaps the constraint or the sensitivity will become more stringent than the results I presented today here. Okay, thank you.
Any questions?
So you count interactions to discover the actions between dark matter and dark matter. And then how could you show this alpha X is always positive?
You mean that always attractive, right?
Yeah.
It could be negative. That means the repulsive. But on the other hand, if it is repulsive, the neutron star has no sensitivity to test this scenario because dark matter simply cannot form black hole.
How about half, like this dark matter half?
So since you have an interaction between this dark matter and the atoms, how do you ensure that the dark matter will just stay on the surface of the neutron stars? I mean, like you capture the dark matter, and then they go into the core of the neutron star.
Oh, in general, where will dark matter go after the scattering is entirely depends on the Vero equations. So this Vero equations describes the allowed region for dark matter inside the neutron star here.
So this means like you have the boundary conditions, then you can determine the inner structure. I don't know. I just wonder why can't they just stay on the surface?
You were also subject to stay on the surface. If the dark matter kinetic energy is larger enough to overcome the gravitational potential, of course, the dark matter particles can stay on the surface. However, on the other hand, if dark matter kinetic energy is not enough, of course, the gravitational potential will pull the dark matter down to the core. So in this case, we assuming that after the scattering, dark matter symbolizes with the neutron star core very quickly. For a neutron star core, the temperature is around 10 to the 5th Kelvin. So such kind of kinetic energy cannot sustain dark matter to stay on the surface of the neutron star. It in principle, be dragged close to the core of the star. And this region is not so big. Perhaps the radius is a few centimeters.